and he has been a great supporter of the group of celestial mechanics in Recife, and by the way, in Northeast Brazil. And he's going to talk about ABC. That's his talk. Okay, Alain, please.
Obrigado, Hildeberto. So I'm very happy to participate in this conference. Of course, I would have preferred after the talk to go with you and Elisabetta in Olinda or in Recife in a good restaurant and hear repentistas, but well, that's life. The talk I present today, as my recent work was not about celestial mechanics, the talk I present today have no new results. In fact, it's a similar talk that I presented 2 years ago in Venice. So if by extraordinary some of you remember this talk, please you can leave. But before beginning, I would like to, as a homage to Hildeberto, to read in my bad Portuguese the end of a poema he wrote to explain his idea of what is a lemma and what is a theorem. So now I read the last part of the poem. Na abstração do fato agora examinado, hipóteses são avançadas como passe em fatos passados, como peça dedutiva pode convir algum lema. E na cadeia de ideias, uma consequência forte pode servir como tese de uma asserção de porte. Neste caso, meu amigo, formula-se teorema. Okay, so now I'll start. So ABC, as I said in the abstract, is for the notation that, at least for the first two with Alain Albouy, we introduced when we studied the n-body problem in higher dimension. And let me start. So my talk will be about relative equilibria and the bifurcations in higher dimension. And let me start with something everybody, I suppose, here knows very well, which is the discovery by Lagrange that there is only a unique non-collinear central configuration of three bodies. Whatever be the masses, this unique non-collinear configuration is the equilateral triangle. And of course, everybody knows the definition of central configuration. If you release the masses without initial velocity, then they just collapse homothetically on the center of mass. So I even, maybe this will be the only proof that I will give, that probably everybody knows. So you just write down the equations of the n-body problem, and you discover that the center of mass has zero acceleration by adding the equations with the proper coefficients, which are the masses. Then you write down what is a central configuration. As I said, you said that the forces and the position with respect to the center of mass are proportional. And then you compare these equations and you find the final equation, which is circled in red. And because you are in non-collinear, the vectors rj minus ri are independent, and hence all the coefficients are zero. And this say that all the mutual distances of the cube or the inverse of the cube are the same. Okay. And you also, everybody knows that each central configuration admits homographic motions, which, and this is another very important result of Lagrange, that they are necessarily planar if you are in R3, they lie in a fixed plane. And the motion of each body is a Keplerian motion, as is written here. So x of t is just the position with respect to the center of mass of each of the three bodies, and it would be the same for n bodies. And the law of the time is just the Kepler law. Okay, and I'll be interested in the case where the eccentricity of each Keplerian orbit is zero, that is the relative equilibria, where the shape is just the bodies rotate like a solid body. Now, if you take 4 bodies, well, of course, everything is the same for 4 bodies. There exists a unique non-coplanar central configuration, which is a regular tetrahedron, and the proof is the same. But there is a big difference that if you are in R3, you have no other homothetic motion than the relative equilibrium. And such motions are possible only in R4 or R6. So now let me introduce the main actors. So this is a way of coding n-body configurations modulo translation that we introduced in a paper by with Alain Albouy quite a long time ago. In fact, in his thesis, he had already a similar notion. Maybe not formalized exactly in the same way, but it's equivalent. So we introduce the so-called space of disposition. So there is not only ABC, there is also D and E, if we call E the energy. D is just the way of coding n bodies on a line up to a common translation. So it's the quotient of Rn by the multi-diagonal. And you have the dual space, which is identified canonically with the subspace, the hyperplane of Rn, where the sum of coordinates is 0. And you have a scalar product that is an identification of an isomorphism between the space and its dual, which is a so-called mass scalar product. And a configuration in an Euclidean space E up to a common translation is just a mapping from this dual space D star to E, where to an element of Rn with sum of the coefficient of the coordinates equal to 0, you associate just sigma of psi I Ri, where Ri are the positions of the bodies, and you see that if you add a common vector to each of these Ri, you don't change the result. And a more sophisticated way of calling this space is just the tensor product of the disposition space with the Euclidean space. And on this tensor product, you have the tensor product of the scalar product on the disposition and the scalar product on the Euclidean space. And this is a classical mass scalar product, which I wrote on the last line. Unfortunately, I didn't work with the iPad because I couldn't connect it to the Mac, so I cannot write. So now, in fact, this is something which was very well known already in the time of Jacobi, because if you take orthogonal basis of both the co-disposition space D star and the Euclidean space, the ambient Euclidean space, and then X becomes a matrix, a homomorphism from D star to E, and the column vectors, that is the images of the basis, are just the classical Jacobi vectors, which are displayed, depicted on these pictures. Okay, so now this is, there are many things on this transparent, but it's just a gram construction. And the gram construction, so recall X is just a mapping from D star to E, or a matrix. And from now on, you can forget about the mass scalar product, or the mu-1 scalar product on D star, and the Euclidean scalar product. You make identifications between the spaces and their duals using this scalar products. And then, so what I call in terms of matrices X transpose times X, this B matrix, so this is the B of the title. In fact, if you want to introduce the scalar products, you look at the first line, and on the first line, I explicited the identifications, but it's just the product of these two matrices. And in the canonical basis of Rn, you can just write this. Of course, we are here from D star to D star, that is from a hyperplane of Rn to itself. And you have this matrix which represents this B matrix. So it's essentially the n-body configuration modulo isometries, but from the side of the bodies, because we are in the D star space. Now you can do the same on the side of the Euclidean space by, instead of this scalar product, this product of matrices, inverting the order. So you look at X transpose, this S matrix, and this is essentially the classical inertia matrix of the configuration of these bodies. And the first one, B, is, as you can see immediately, is invariant under the orthogonal group. If you change the configuration modulo rotation, you won't change this B matrix, but you'll change the S matrix. This is well known because it's the configuration of inertia which rotates, but it's invariant under the orthogonal group of the other space, the co-disposition space. And this is this group is known by physicists, and it was called the democracy group by the physicists. Okay, so that's the first actor, this B matrix. And now come the A matrix, which is on the side of the forces. And this we had called the Wintner-Conley endomorphism. So don't look at the two. It's just a question of because it was written like that. You call 2A this matrix, and it's also a mapping from D star to D star, which is symmetric from this for this mu minus 1 scalar product. And it's just a simple trivial exercise to see that if you look at the Newton law, so-called Newton law, the differential equation of the motion, then you can write it like that in terms of matrices, and you get this matrix, which is a matrix from Rn to Rn, and which is a unique extension of this A matrix, or 2A matrix, from this hyperplane where the sum of coordinates is 0 to itself. And it's a unique extension which sends the vector whose coordinates are the masses onto 0. Okay, this is A. So we have already A and B. And it's important to remember that the motion, the equation of motion are just written in this compact form, x double dot equal to xa. So you can forget about the two. It's not significant. Okay, now, if I had used a tablet, I would have made the exercise on the board. The interpretation of this matrix A is just a fancy way of coding the derivative of the potential. If you call U hat of B the potential as a function of the matrix B, the matrix, one important thing which will come after is that the matrix B and the matrix A, in fact, depend only on the mutual distances. And so in terms of information, it's equivalent to give the matrix A or the matrix B. And you can, the potential, of course, is a function only of the mutual distances, that is of the matrix B. And if you consider it as a function of the matrix B, then its derivative is just given by this simple formula applied to a tangent vector to the space of B matrices. It's just a trace of A delta B. So this is the interpretation of this matrix A. This is the derivative of the potential. So now come the equation of relative equilibria, that is of rigid motion. So this is a theorem which is in this paper with Alain, and which characterizes, it's a generalization of Lagrange, it characterizes the relative equilibria in a space of higher dimension. So when I say that the dimension of E is 2p, it means that E is a real dimension where the motion really takes place. You have no extra dimension which are not visited. Then it must be of even dimension, and you must have an epsilon anti-symmetric rotation matrix, which is a non-degenerate and independent of t, such that the motion x of t, remember x of t is this element of D tensor E, or homomorphism from D star to E, which characterize the configuration up to translation. And this x of t will rotate like a solid body. You have e to the omega t x of 0 in time of t. And it's important to notice that omega is independent of t. I say that because in a review paper that I had written, the referee wrote me that he didn't trust that omega was independent of time, and I had to give him the proof that really it is. But I won't do that now. So now you write again the equation as I wrote then. So you are interested in relative equilibria, that is well, of course I showed the screen, but you don't see it. You don't see my finger. X of t, so if you take the double, twice the derivative of e to the omega t x of 0, you find that x double dot equal omega square x. And as I said before, by definition of this matrix A, it's also 2xa. So now you can do exactly the same construction as we did with constructing the matrices B and S. On what I call the side of the bodies, if I multiply by x transpose on the left, I find that x transpose omega square x equal to x transpose xa, that is 2ba. And if I do that on the other side, I multiply on the right by x transpose, I find that omega square x transpose, that is omega square s, equal to x transpose. But both x transpose omega square x and 2x transpose are symmetric, hence equal to their transpose. And this implies that on the left, on the side of the body, the commutation of the matrices A and B for a relative equilibrium, and on the side of ambient space, the commutation of the matrices omega square and S. So I wanted to give the proof of what follows on the screen, but as I couldn't use the iPad, I won't do it. It's a simple exercise to prove, and I'll use this later on, that in fact this, which is in this paper with Alain, this is a characterization of what we call the balanced configurations, which are more general than central configuration, and which in higher dimensional space can have relative equilibrium motion, but not homothetic motions with different eccentricity, just relative equilibria. And the characterization is that this matrix B, which characterizes the shape up to isometry, is just a critical point of this potential, considered as a function of the configuration, restricted to the isospectral manifold, that is, to all these symmetric matrices which have the same spectrum as B. And the proof is very easy. You just write that having the same spectrum means being conjugate to a rotation. You write the derivative, and you use the fact that when you take the trace of a product, you can change the order of the factors, and you find that in fact for any anti-symmetric matrix, the trace of this commutator AB times any anti-symmetric matrix should be 0, and by non-degeneracy of this trace form on the anti-symmetric matrices, this proves that this is equivalent to the commutator of A and B being 0. Okay, and this is to be compared with the classical characterization of the central configurations, which are when you fix the rank of B, that is the dimension of the configuration, just the critical point of the potential restricted to the moment of inertia, which is constant, and that is only the you fix only the trace of B and not the whole spectrum of the matrix. And of course, this is the same, and this is also classical. Well, this is a way of saying a classical fact that being a central configuration is equivalent to the restriction of the matrix A to the image of B being a multiple of identity. That is, all the eigenvalues of A restricted to the image of B are equal. And this implied that the rotation, in this case, for a central configuration, must be just up to a constant, a complex structure. The square is minus identity up to a constant. So that's the big difference between the relative equilibria of central configurations and the relative equilibria of balanced configuration, that the first ones are necessarily periodic, while the other ones are in general quasi-periodic as a general rotation in higher dimension. Okay, so now comes really the problem I wanted to address. That is, you take a balanced configurations, and the problems we ask is what kind of relative equilibrium motion such a balanced configuration may have. That is, how many frequencies for this quasi-periodic motion, and in what dimension it can have such a relative equilibrium motion. We know that this ambient space must be even dimensional, but we have to determine what is the minimal dimension, for example, in which you can have such a motion. You see, for example, that for the we'll see that after. There is either. Okay, so let's take any balanced configuration. Then we know that the matrices A and B commute, and also the matrices omega square and S. So we can find respectively in the space D, in the space D star and in the space E, we can find orthogonal bases which diagonalize simultaneously these matrices. So I have written here the matrix 2A. We know that because the Newton force is attractive, it's a negative eigenvalues, minus lambda 1, etc., minus lambda n minus 1. N minus 1 is a dimension of D star if you have n bodies. Then B, it's a diagonal matrix B1, B up to Bn minus 1. Omega square is a diagonal matrix minus omega 1 square, etc., minus omega d square. And where D will be the dimension of the ambient space, that is 2p. And S also is a symmetric matrix from E to E, if you identify E and the dual, and it's I call the eigenvalue sigma 1, sigma d. So now it's also a simple exercise. You look at this matrix X, which goes from D star to E, and which represents the configuration up to translation. And as we are in eigenbasis, the image of B is generated by eigenvectors. So and the image of S, I'm sorry, is generated in E is generated by eigenvectors, and the image of S and the image of X are the same. That's a classical exercise. S is just X transpose, and hence a priori X is you can choose a basis so that the basis of D star, so that only the first lines be non-zero, and the last lines will be 0, where the number of non-zero lines is just the dimension of the rank of the matrix S. But now you write down that, moreover, the omega square commutes with S, and you find that no, you just write, sorry, that S is diagonal, and then you'll find that X must have this form where you have an invertible matrix V, which is of the dimension of the rank of S, or the rank of B, which is the same, and the other terms are 0. And now, after possibly permuting the basis of D star, when you write the equation that X double dot equal 2XA, then you find that, in fact, up to a permutation of the basis, the eigenvalues with a minus sign of omega square must be equal to the first, that is to the first eigenvalues, to the first eigenvalues in number the rank of B, or the rank of S, of the Wintner-Conley matrix. That is this equation omega I square equal lambda I. That is, the Wintner-Conley matrix gives you the spectrum of this matrix, gives you the way this balanced configuration will rotate. That is the instantaneous velocities, omega I square. So now let me take an example. This is the example we shall look. Take four masses, and I'll suppose that they are generic. That is, that the ellipsoid of inertia has 3 different principal axes. That is, the eigenvalues sigma 1, sigma 2, sigma 3 are different. And in fact, it's sufficient that not 3 masses be equal among the 4. So we have this tetrahedron, and suppose that not 3 masses are equal. Then you have this property. And now you have 2 possible cases according to the eigenvalues of this A matrix, which is essentially the derivative of the potential as a function of the configuration. The first case is the case where the 3 eigenvalues. So here it's the dimension of D star is 3. So it's all the eigenvalues of the matrix A, which goes from D star to D star, and you suppose that they are all distinct. So if they are all distinct, are the instantaneous rotations of the matrix omega, which characterize the rotation of your relative equilibrium, they must be different because they are equal to respectively lambda 1, lambda 2, lambda 3. So you cannot have a rotation which concerns at the same time 2. So the U1, U2, U3 are an eigenbasis of S, which is also an eigenbasis of the square of the rotation matrix. And as the lambda I are distinct, it's impossible that 2 of these eigenvectors be concerned by the same rotation. So it means that the only way to having this rotation will be in a 6-dimensional space. And in this 6-dimensional space, you have the 3 eigenvectors of S which generate the 3 space generated by the tetrahedron, and you have 3 more dimensions, and you may put together one eigenvector of S and one extra orthogonal to the three-dimensional space vector of the one of these three extra dimensions, which I call V1. And in here, you'll have a rotation omega 1. And then the same for the two other eigenvectors, omega 2 and omega 3. And you have a rotation matrix with these three different eigenvalues, and I omega 1, I omega 2, and I omega 3 for omega, and which will correspond to a rotation of your balance configuration in R6. But if, on the other hand, you have a balance configuration which is such that two of the eigenvalues of this matrix A, the derivative of the potential, which are equal, then you can have a different way of rotating, and you can rotate either in R4 or in R6, but you can, this time you can rotate in R4 in the following way. You can associate, for example, U1 and U2 if lambda 1 equal lambda 2, and then you have a rotation in this plane generated by U1 and U2, which is in the space generated by the tetrahedron, and then you have a different rotation, omega 3, in the space generated by U3 and an extra fourth vector orthogonal to this 3 space. But of course, you can also have a rotation in R6, where you'll have, for example, such a rotation omega 3 in the plane generated by U3 and V3, but you can have also a more complicated rotation in a 4-dimensional space generated by U1, U2, and 2 extra vectors orthogonal to this 3 space with the instantaneous velocity omega 1, which is equal to omega 2. So there are, in this case, the two possibilities, R4 or R6. And now, the last part of what I want to say concerns so in what case can we have this equality of eigenvalues of the matrix? And in fact, this comes from a wrong idea that I had at the beginning. I thought that you know that for symmetric matrices, this is a classical fact. Having an equality of eigenvalues is a codimension 2 phenomenon. It's not a codimension 1 phenomenon. But in fact, here it will be a codimension 1 phenomenon, and I explain why. So here so it's a pity not to be able to write down. So I put myself in the common orthonormal eigenbasis of B or B0 and A0 at the time 0, the configuration B0 and the forces A0, which I remind you are in this 3-dimensional space, which is the co-disposition space. And I suppose that the masses are generic in the sense that the eigenvalues of B are all different, are all distinct. And of course, up to permutation is the same as the eigenvalues of S. So this means here the genericity means that there is a unique rotation which puts B into a diagonal form. So I call it R. So RB R minus 1 is just the diagonal matrix B1, B2, B3. And of course, because A and B commute, this rotation R also diagonalize the matrix A. Hence, RA R minus 1 is the diagonal lambda 1, lambda 2, lambda 3. So now this big phi, which is in the middle of the screen, which I call DFO outside of collision, it's just saying that the information on the B matrix and the information of the in the A matrix are the same. It's just the information of the mutual distances. Knowing B or knowing A or knowing the mutual distances is the same. So you have a diffeomorphism from the space of all B matrices to the space of all A matrices. And now I'm interested in some, I suppose that B0 is a balanced configuration. And we know that it's a critical point. And in fact, and I take not only a balanced configuration, but I take a central configuration. And so I know what it is. It's just the regular tetrahedron. So it's unique. And I know by the characterization I recalled that it's a critical point, and hence necessarily isolated, of the isospectral manifold. Isolated because I already quotiented by all the isometries when I look at the matrix B0. So I have an isolated critical point in this isospectral manifold, which I, on the picture on the left, it's depicted. And of course, if I look now at the balanced configurations, which are closed to the central configuration B0, they are also they are characterized, in fact, just by their eigenvalues, just because of this spectral characterization. If I just go along the isospectral manifold of some balanced configuration, I won't find another one because it just I'm going away from the critical point. So the balanced configurations are just parametrized by the eigenvalues of B when they are close to B0. And I'm interested in the ones for which the eigenvalues of the fourth matrix, of the A matrix, will be equal to know which could bifurcate to know which could rotate in a smaller dimensional space in R4 and not in R6. And so for this, I look at, on the other side, but I say that if I go from the space of balanced configurations on the B side to its image by this mapping capital phi, then I have this diffeomorphism, and I say that this gives me a diffeomorphism. I can parameterize the image of these balanced configurations. I can parameterize the image just by the eigenvalues of the matrix A. And the computation is just the following. If you look at the unique matrix, so by hypothesis, because the masses are generic, there will be a unique matrix for a balanced configuration close to B0. There will be a unique rotation, which I call R of B, which diagonalize which diagonalize B, which diagonalize the configuration matrix of this balanced configuration. But it's also diagonalize A. This I know because the two matrices commute. Hence, I can look at the mapping which to a balanced configuration B associates the unique rotation which diagonalizes B times A times the inverse of this rotation. And I know that this is a diagonal matrix. This is a diagonalized matrix lambda 1, lambda 2, lambda 3, because it diagonalizes A. And now I say that this mapping, which from B to the diagonals, or to lambda 1, lambda 2, lambda 3, is a diffeomorphism. Because if you compute the derivative, then you have first the part where you take the derivative of A with respect to the variation of B, but capital phi is a diffeomorphism. And you have another part which comes from the commutator of the tangent vector to the rotation, where you vary the B and the matrix A at the central configuration B0. But A0 is a multiple of identity, so it commutes with everything. So this disappears, and in fact, you have a diffeomorphism. So this proves that on the left, you are parametrized by the eigenvalues of B for this balanced configuration, and on the right, you are parametrized by the eigenvalues of A. And hence, having two eigenvalues equal becomes, in this subspace, of course, a phenomenon of dimension 1, just the equality of two coordinates. And so, hence you have the three subspaces which correspond to these matrices, which can have this, which give you on the, when you take the pullback by phi, you have these three subspaces which correspond to balanced configurations close to the regular tetrahedron, which have the property that they admit relative equilibrium motion in R4 and not in R6. So now the last part, which I want to just to browse, is the characterization in terms of angular momentum of this relative equilibria, and in particular of what, when you have a central configuration, so take, for example, Lagrange equilateral triangle, or the regular tetrahedron of 4 bodies. So when you when can you take such a relative equilibrium and you ask whether it can bifurcate to a quasi-periodic relative equilibrium of a balanced configuration, where the shape, the configuration will change, will become only balanced and no more central. For example, you take your equilateral triangle and you change a little the shape to be balanced, and you ask when, how can you read, particular on the angular momentum, how you can, when you can bifurcate from this relative equilibrium of the central configuration to a relative equilibrium which will be quasi-periodic of a family of balanced configurations. So here I write down what is the angular momentum, and in terms of this X matrix, recall from D star to E, or in D tensor E, which characterize the configuration up to translation, the angular momentum is just, you can consider it as an anti-symmetric matrix. It's minus x dot, where x dot means velocities transpose. So it's x dot is a configuration of velocities up to translation, and plus x dot times x transpose. And as you started with a central configuration, so you know that for a central configuration, the relative equilibrium is given by a hermitian structure, by a complex matrix, where the J matrix has square equal to minus identity. Then, and if S0 is just the inertia matrix of the configuration at time 0, and then you have this formula where it's more pleasant to write down the formula of the angular momentum as omega. So you can forget the omega, you can just normalize things so that omega equal 1. and times J hermitian. So the hermitian for the J complex structure matrix, which is J minus 1 S0 J plus S0. So this is a formula for the angular momentum. And of course, we are interested in things only up to isometry. We are interested in the spectrum of this angular momentum. So if I look only at this J hermitian matrix, so there won't be the square root of -1 everywhere. So I call the frequency map the map which from J goes to the spectrum of this J hermitian matrix. So I call it a new one, greater or equal, etc., greater or equal to new P. And a theorem which we had proved with Hugo Jimenez Perez, a Mexican colleague, is that the image is a convex polytop. So I won't tell you why. In fact, it's related to the Horn problem and to moment maps, but it would be another talk to explain this. And one obvious thing is that the spectrum of this matrix must satisfy this quality, that is the sum of the eigenvalues is the moment of inertia with respect to the center of mass, the trace of matrix B or the matrix S, it's the same. Of course, if you consider this matrix J minus 1 S0 J plus S0 as a real matrix, you'll have twice, each eigenvalues will appear twice. So here it's the eigenvalues as J complex matrices. Okay? And in fact, an important information about this spectrum is that it's not necessary to find the image of this. So we are interested, when you look at this image, it means you are interested in the behavior of the angular momentum for all possible relative equilibria of these central configurations, which amounts to changing the Hermitian structure, the J. So in fact, it's enough to look at very special J, which I call the adapted complex structures, to understand the image. And in fact, if you order the spectrum of the inertia matrix sigma 1 to sigma 2p, 2p is the ambient dimension, and you call u1, u2p an eigenbasis of this matrix S, S0, then it's enough to look at the complex structures which have the following property. You take the middle dimension, the p-dimensional subspace generated by the eigenvectors u1, u3, etc., u2p minus 1, and you look at the complex structures which send this subspace of dimension p to the orthogonal subspace of dimension p generated by u2, u4, etc., u2p. They are very special, and in fact, you can prove that the image of this frequency map, that is all the possible ordered eigenvalues of angular momentum of a relative equilibrium of this configuration, are the same as the image of this special complex structures, and this is a so-called Horn polytop. That's exactly the spectrum of all possible spectra of a sum of P by P matrices whose spectra are respectively this half of the first half of the spectrum of S0, sigma 1, sigma 3, etc., and the second one, sigma 2, sigma 4, sigma 2p. And if you can take other types of complex structure which are associated to a division of the spectrum into two equal parts, but the other subdivisions in two parts give sub-polytops. And it's not a partition, it's more complicated. They can have intersection, but they are smaller a priori than this one, which gives the whole image. So now, just to conclude, probably this was much too quick if you never saw this. Let me just show you what can be said as a result in the two cases of 3 bodies and 4 bodies, that is for the equilateral triangle and the regular tetrahedron. So for the equilateral triangle, I put myself in R4, which is the highest possible dimension in which you'll have relative equilibrium motion. And you have the following. So recall the trace of the spectrum of the angular momentum, nu1, nu2, is fixed, it's inertia, moment of inertia. So we are on a line. And the image of the frequency map is just an interval between these points A and B. The point B corresponds to nu2 equals 0. That is, one of the frequencies of the angular momentum is 0. It means you rotate in a plane, and you don't look at the other part of this 4-dimensional space. So B is a Lagrange solution. But from here, you cannot bifurcate to relative equilibrium of balanced configurations with which would be quasi-periodic with 2 frequencies. The only possibility of doing that is to be at the other extreme of this polytop, which is the matrix A, which will correspond to the only relative equilibrium motion where you'll be able to bifurcate to a quasi-periodic relative equilibrium of a balanced configuration. So this would be also the case for even for equal masses. Then the point A would be on the diagonal, and the balanced configuration in this case would correspond to isosceles triangles. Then in this case, you can bifurcate in R4 to quasi-periodic motions of isosceles triangles. And for the case of the regular tetrahedron, it's a little more complicated. In the small drawing on the lower left of the drawing is this polytop, the image of the frequency, the possible frequencies, ordered frequencies nu1, nu2, nu3 of angular momentum, of a relative equilibrium of the central configuration of the regular tetrahedron. And then by this analysis, you can show that the only motion from which you could bifurcate with 3 frequencies in R6 is the point A. And that is, it's only with these 3 frequencies, nu1, nu2, u3, given by the point A of angular momentum, that your relative equilibrium motion periodic of your regular tetrahedron may bifurcate to a quasi-periodic motion with 3 frequencies in R6. Now the red lines, one broken line on the left from A to B, and then the line from A to D and the line from A to C, correspond to motions to eigenvalues of the angular momentum of this periodic relative equilibrium of the central configuration of the regular tetrahedron, which could bifurcate in R4 with 2 frequencies only. And the point B, D, C, which correspond to nu3 equals 0, so the motion lies in R4, and they are the only values of the eigenvalues of the angular momentum for which you can your relative equilibrium motion can bifurcate to a quasi-periodic motion of balanced configurations in R4 and not in R6. Okay, so I end with two questions that I'm unable to solve. The first one is if you want to generalize this reasoning of the corresponding of the way to parameterize the balance configurations by the eigenvalues of the matrix A restricted to the image of B is this map from balance configurations to its image local diffeomorphism. And the second question is an old question, if there exists a balance configuration of 4 equal masses which have no symmetry. So this is, of course, a question for Alain, but I don't know the answer. Okay, so I really, feliz aniversario, Hildeberto. I really apologize for probably an incomprehensible lecture because I couldn't write on the blackboard and show things on the screen because of the poor technique of not being able to connect the iPad to the computer. Okay.
Thank you, Alain, for the talk. And, is there any question or comment?
Could you explain what's special about the point B in your equilateral triangle diagram? I mean the point A. Why is that the only point where you can bifurcate?
Yes, let me. In the point A, you want to recall this picture here. You want to be in this case, but with more two more vector because no, it's exactly this picture. You want to have this 3 different eigenvalues where you rotate in this way with 3 different frequencies, and not to be in this case. And then if you look at the spectrum of the angular momentum for such a configuration, you see that this corresponds to this what I call these spatial complex structures, where you take half of the space of dimension 3, and here it will be the space generated just by the tetrahedron, that is by U1, U2, U3, and the complex structure will send this space to the orthogonal space generated by V1, V2, V3. And then the frequencies of the angular momentum are just the spectrum of a sum of 2 matrices whose spectra will be respectively sigma 1, sigma 2, sigma 3, and 0, 0, 0. So in fact, the spectrum is just sigma 1 plus 0, sigma 2 plus 0, sigma 3 plus 0. So it must be the point sigma 1, sigma 2, sigma 3. And this is the point A. So this is the reason.
Okay.
Hello? Jeff, do you have a question?
No, I'm just telling Alain to use something called air server. Then you can use.
Yeah, I know AirPlay, but the problem is because the lab didn't give me a more modern Mac. My Mac has only the software, how it's called, Mojave, and not Catalina. And if I have not Catalina, I cannot have AirPlay. So they promised me that maybe with a connection I can do that, but for the moment I cannot. So that's the reason. Does this answer your question?
Yeah, okay.
So maybe Alain needs a GoFundMe page for a new Mac. Is that what he needs?
Right.
No, but they already offered me an iPad.
Then you can start a GoFundMe. We're poor mathematicians.
So that's the reason why it was so messy.
Okay.
Okay, any comment and question? So I thank the speaker again.
Okay.
Yeah, you should.
Yeah, I have a question, I think. Hello, Dave. Dave?
Oh yes, I make a perhaps stupid question. There are topological ways to study equilibria, since the thesis of Hildeberto, for instance. For these general types of more general than homographic that we call balanced, topological tools, are they possible as a tool to study them?
Well, I suppose it's the same tools as for central configurations. You are looking at critical points. You want to do some more theory or things like that.
Has it been done, or is it worth for young people to do it?
No, well, I think it would be worse if there were some concrete applications. So I'm not sure it's worth to ask young people to look at this unless they have a special idea.
Okay.
Okay, I have. So Alain,
Yeah.
So the central configuration and relative equilibrium in your case is defined to be the distance has to be always the same.
In this case, yes, because it's a unique. I was interested in this simple case of the regular tetrahedron. So in for 4 bodies in R3, there is only one.
Right. But so relative equilibrium is defined to be where the distance is always kept the same. But the central configuration.
No, of course, it's like a solid body, yeah.
Yeah. Okay. But actually, it's a solid body. But a solid body moves in high dimensions in various directions or rotations. So basically.
Yeah. Yes. Yes.
Okay. They don't have
central configurations also. No, of
course.
The
whole point is they don't have to be central configuration.
No. Of course, but but they have to be balanced configuration. If they want,
so it's a
if they want to move.
That's not necessarily a central configuration.
Of course not. No.
Okay, all right.
No. For example, for three equal masses, this is the case we had studied with Alain. This is the simplest case. Then the balanced configurations are all the isosceles triangles.
Okay.
And they can have a quasi-periodic motion in R4.
Yeah, for that. Yeah. Okay. I see. So for 3 equal masses, that all equilateral triangles are actually relative equilibrium.
For 3 equal masses, you have only the Lagrange and Euler central configurations. You know that. Whatever be the masses.
Yeah. Okay.
And for balanced configurations, there are drawings in our paper with Alain where you see in the space of masses how are of triangles how are the balanced configurations. And Alain and Delin recently wrote papers on that also.
So typically they are not isolated in configuration space.
No.
Yeah,
no.
So they are continuous.
No, of course not. Basically. Of course not.
Yeah.
And when you bifurcate, you'll have change of configurations. Yeah.
Right. Okay. All right. Thank you. So what typical are the dimensions of these continuums of the balanced configurations?
I have not that in head, but it's not. Well, see, typically that you see that the number of the rank. Look at this picture.
Yeah.
Here they are just characterized by the so it's the rank of B which tells you.
Okay, so generically, that actually can compute this rank easily.
Yeah, yeah.
Okay. Thank you.
Okay, Annette, then we pass to you.
Yeah. Now we going to see the vignette from the conference. Okay, so Alain, I will stop your presentation. Start
Yeah.
this one, okay?
Yeah. So should I do it, or are you doing it?
I can do from here. It's okay.
Yeah. So please do it.
Okay. Could you see it? Something coming? Could you see?
I should click.
Yes.
Thanks.
Yes, we see.
What should I do?
Okay, so thank you, everybody. I think that we can stop the recording, Marcelo. Just some information for tomorrow.